the screen, I'm recording on my hard drive. So the idea is with this, if my feed goes bad, which, let's face it, it's the internet, and the amount of people using Microsoft Teams, it's through the roof. So I use my hard drive to record, and that ensures that that feed is seamless. However, if I use Stream, it can go a bit hazy, and I would rather not risk that haziness. So that's just to let you know that it is recording, but you don't see it for that reason. Right, so I want to pan back to something that we talked about last week. So let me just go back. So you notice here, I left this out. I was just interested who would take a look at it and dissect it. This is your second order simulation. So under a first order, you have your simple two-component interface. So you've got your, in this case, it was a spring and a damper. You could relate this to the door mechanism or any different types of things. Once you bring on the third component aspect to this, a second order aspect will be introduced. So you'll end up with oscillations. So if you drop a mass with a spring and a damper attached, that behaviour will be related as from the momentum coming from the mass itself. So you'll get that that if you were to plot it, it will be a down, up, down, and you get that overshoot and oscillations occurring. So I only put it on there. It's not essential for what we're doing, but it's a really, really common problem. 2 seconds. Ah, right. Okay. Right, Josh. Yeah, I will do that. Let me see if I can stick it on. Ah, yeah. I'm glad somebody's actually pointed that out. It's funny because I forgot about this. I do know some companies will not access and allow YouTube to be used as a system, so that's fine. Let me find an alternate, because obviously you guys, like everybody else, like some who are also in work, won't have access to that. So let me fix that, and I will sort that out, because that explains an equivalent question that we had in a meeting earlier. Because you guys won't get it. Apologies for that. That is me totally forgetting that places like your employment won't allow for things like that. So yeah, let me sort that out for you. Right. That's a swine, is that? Right. So where was I? Oh yes, yes. So on the second order system. Under that second order system, the typical way that you'll get the appearance, is it going to let me just, oh, I have to download it. It's alright, it's alright. So that's your typical second order system, how it's drawn. If you've done this, I don't know if you've done this yet with Akinola, you probably will do, you will cover this. So that's your typical mass spring damper. I've given all the equivalent. Now these are Euler methods. Now granted, with Euler methods there are a lot more accurate terms to be used, but this is a nice approach to just giving you an outside of 2 seconds. I think I had a question come through. So and there are a lot more accurate ways to solve this. With this though, it's a nice iterative method. Now the iterations is what I keenly wanted to consider. So we've got the zeta value, we have our over dampings for the effects coming from the natural damping effect. There's a lot of things that occur within here. Now that's just the method for solving this analytically. What I wanted to do is actually approach this from a solution within the software itself. Try and show you where each element of these equations are accumulated within the software. This is just a nice basic setup. This is just a nice introduction to navigating around this system and seeing how this system works. So, Solidworks Motion. So under the Solidworks system, the normal Solidworks system, there's a few things that I can start to do. Now, as I said, first things first, I'm going to try and solve the solution for a second order system. I'm going to try and look at getting a second order system to be operatable in this type of dynamic. Now, Solidworks, well, Dassault, Dassault pay a license fee to use MSC's solver, which is Adams. Adams is one of the biggest solvers. You'll find it in MATLAB, you'll find it everywhere. It's a big numerical solver, but they use Adams as solver for this. And what I'm going to do is take you through these elements now. So I'll go new, and I'm going to go assembly. The mass that I'm using for this, I've already modeled and I've already put onto Teams. Those of you who have this already open. So on Teams, you'll find a model just called mass. So all I'm going to do is I'm going to insert this mass into the actual workspace and click OK. Now the way that I've modeled this, for anybody who's curious, the way that I've modeled this is I've done a center rectangle, and the size of this is based on the equivalent of what we did yesterday in MATLAB. Now in MATLAB we chose a mass which was 50mm by 50mm and by 50mm. And this mass is done the same. Now the reason I did a center rectangle is because the way that these systems approach the fixtures is... have we got another question coming in? No. So the way that they approach these systems is it's where that it's being drawn. So it's its origin in which it's starting from. So if I click on origin, you'll see there that that's how it was done. So I did a center rectangle and I've simply extruded down by 50mm. The important element about this now is we need to tell it how it's going to move. Now if we look at the original notes that I've given you, this is where the limitations of Euler's method comes in. If you look at how it's equated, you look at the second order for the way that the force is taken into consideration by the spring stiffness, and also where's my zeta coefficient? So my damping coefficient, you look at where these are. What they're actually referring to is the equation of a line. So if we refer to the equation of a line, that instantly implies that whatever method that was used to solve this is actually being done by restricted vectors. It's not allowed to move in a three-dimensional space. So what I would do with that is I could consider simply this. All I'm going to do is I'm going to constrain it not to be able to move in particular spaces. So you'll notice there and there, let me go there and there, you swine, there and there. If I spin that round, you can see there that it's actually sitting on there. But once I run a simulation like this, in fact, before I actually make any changes, I think it's better if I actually show you what this problem is that I'm talking about. So, when systems bring models in, any Dassault, any Autodesk, any major CAD systems, what they tend to do is they put in a groundwork of any system that you'll introduce. So what I mean is the first component that comes in tends to be fixed. So what I'll do is I'm going to set that to be floating. What that means now is if I drag it, it will move anywhere that I want it to move to. So it can be free to move whatever. What I'm going to do is, I think, we'll try and run it from this space. So first things first, if I bring that in, this is what's been highlighted, especially to me this morning. So again, I'm apologetic that I can't solve this right away, but this morning it was highlighted to me that if I go to my options, go to add-ins, this is not appearing for everyone. So this is what you should be looking at, as the email I got this morning does show that it's not. Now these are all just things I'm running on the background, but these are not appearing for everyone. So again, please bear with me. I've got to figure out where that's coming from now. It's been a continuous chain of things not functioning like I wanted them to, and I need to find out why it didn't appear for said students this morning. So I'm going to click on SolidWorks Motion, and I'm going to click OK. Now there is a misbelief. I say misbelief. There is a misbelief of how these are set up. I do need to save this first off, so I'm just going to click on Save As, and I'm going to save this into here as Mass spring damper. For anybody who's unsure, when I produce these, what I will also be doing is I will upload these models onto Teams, and if you need them, if you kind of go, what's that thing that we're doing again? If I upload this, it means that you can grab it, take a look at it, then dissect it, and then think, oh right, yeah, I remember. So, and again, I do want to just push that if you do need to speak to me, Teams is dead easy to get in touch with someone. So if you can, just get in touch, or email me. But if you email me, put MP3672 in your email, because then it filters out the billions of emails that I get from advertising companies. So what I've done is gone on to Solidworks Motion. This now is an animation. This is not a good true dynamics tool. This does not use the Atom solver. This uses a basic principle of it. So interestingly, those of you who didn't get Solidworks Motion, if you click onto here anyway, when I click this tab down, you may see basic motion. Now under basic motion, let me just see if we can solve this under here. We may be able to solve this, just for you to follow me along with this. But what I'm going to use is I'm going to use the motion analysis. Now you'll notice when I clicked onto motion analysis, we've now got the solvers for SolidWorks simulation. This is because you can have a dynamic system running, and if there is a key particular point where you want to consider the stress that's occurring around a closed system component. I refer to a closed system as something where you've got key mechanical components where they're all working together, but there's a relationship, and the relationship doesn't change. So think of a crank, conrod, and a piston to cylinder. Basically, they're all interconnected components. So that's what I refer to as it being a closed system component set. Right. So from here, now, I'm just going to pan back to my drawing. The only reason I pan back to this drawing is I do like to stay with these notes, because you guys have got this. And if I start mecking this up, it makes things confusing for you and for me as well. So, we've got the drawing, we know we need a spring, we know we need a damper, but we've already got the mass. Now, what I'm going to do is set up the basic one first, and I want you to see some of the issues that arises. Those of you who went through the solution for the second order system, I'm going to load that solution today. I did it on MATLAB, I've done it on Excel, same process that we used last week, but it will allow you to really dissect exactly which way I'm going with this. So I'll upload that today, and you can see this to your heart's content. 2 seconds, just had a quick question. So, the question is about where do you find the recordings? Now I know I've just had a question about the recordings from industry guys. That's totally with you. I will sort that out today. But the question about the recording, where you will find it, go onto Blackboard and then go onto recorded lectures. You should find all the pre-recorded elements on there. If you do have, apologies, if you don't have YouTube access, or you're under a company, which obviously a lot of companies are, they restrict that YouTube access, please let me know. I mean, I'm going to solve that problem today anyway for everyone else. But that is where you will find it. It's all on Blackboard under the recorded sessions. If you are looking at the recorded sessions, you will find this example as well. Not saying you have to stay for this. What I'm saying is that I'm working through the exact same example that I did yesterday. So, we know from this we need a spring. So what I'll do is I'm going to choose there, and I'm going to choose top plane. Now what you'll see is nothing. This is appearing because the plate is infinitely sat against the top plane. I mean, I can click OK, and you still look and you go, not sure what I've done, not clear at all. What we really need to do is we need to move that down slightly from that top plane. Give it that distance, because if we're going to use that top plane as our fixing point for the brick itself, or for the fixed point, then what we really need to do is set that up correctly. So what I'll do is I'm going to go to I'm going to make this, but then I'm going to suppress it. So if I go top plane, and then I go top of the face, and then I go, let's go distance. So what I'll do is set this to, I'll go 20 millimeters. Oh, flip that down, flip the direction, and then click OK. Now I know it doesn't seem much what we've just done, and it's not much what we've just done. All that's actually done there is it's just moved it down, and if I go to my top plane, but the issue is now it's restricted. So all I simply do is I'm going to suppress that. So I'm going to suppress that out completely, and then go back to my motion analysis. So you'll notice there it's suppressed, and if I go to my top plane, oh, it's still not updated. So let me see if I can update. This has happened to me a few times before. Right, let's just go to create a new motion study. So if I now go to top plane, there we go. That one just wasn't updated. So all I've done is just created a new motion study. I've just done the same thing again, and it's just to get it so I've got that distance. So I've got a true distance of where it's coming from. You'll notice as well, it's made itself center rectangle just a slight offset from the actual brick itself. So that works well for us, really well for us. So what I will do is I'm going to turn that on so it's visible. And let me just go to here and turn my planes on. And now I've got a visible plane beneath. Now what I can do is go spring. Go here to here. Now what you'll see is a simulated spring. Now for those of you who have seen Nastran before, Nastran is MSC's golden egg. It's a phenomenal simulation tool, but Nastran does the same thing. This is where MSC Solutions takes over, and these are the approaches that you can do. So down here, what do we get? We get the linearization of that approach to the spring itself. You can, for anybody who's interested, you can change the display. You can make it bigger, make it smaller, you can make it as a true representation of what that spring is actually doing. You can give it the overall radius and obviously coils to fit, but do be aware of that this is simply a display. It is not the configuration for it. The free spring length, you'll notice there, is set to 20 millimeters purely because I'd moved it by 20 millimeters from top plane to the top face. So it sets itself to that. But I can change that if I wish. I can make the free length even more, so you'll get even greater overshoot of the spring itself. The spring stiffness, we can change units if we wish. I often, like everybody who's probably in this meeting, I always run all my units in millimeters. I have obviously come across some people from the States who obviously don't run in that. They run more in inches. Which, yeah. But for us, we're staying with a linear spring. If you have a torsional spring, you can approach it that way as well. I'm not going into a lot of using on these just because I want to treat this as this is the environment of what we're operating in, and this is what our approach is. Now finally we have here the damping. This is a natural damping of the material. You can refine that natural damping of the material, and you can get the material to respond and then add a damper on the top to try and make your result as more accurate as possible. It is a fascinating way of doing it, and it is slightly different the way that they do it, but it is a good way of doing it. I don't tend to use it because the thing is if we compare again against the mass spring damper problem, you actually cause about, I mean, we have natural frequency changes. Obviously we have the natural frequency changes, but this is actually equated not through the spring. it's coming from what was our original zeta value in the first order. So, well, at least a derivative of the spring value of the first order. So I'm not including that on this. So if I click OK, we've now got a free spring. So if I just save that, and then the other thing that we need in this case, because our active force is simply going to be F is equal to ma. So we know that what we're going to need for this is a material. So I'm going to go right click, and I'll probably just use your standard off-the-shelf material, which tends to be a plain carbon steel or a cast alloy steel. I always go plain carbon because it's always the default one that most software seem to go to, or some form of steel. So Inventor, CATIA, they always seem to default themselves to these. Right, so if I simply, all I'm going to do is calculate this now just to see if everything's active. So if I run it, so nothing occurred, purely because my F is equal to ma. In other words, I didn't stick gravity on there. So I'm going to click onto gravity and then go Y. If you look onto my Y, I can choose gravity effects. I can say which way I want it to move, what is the key point to influence this gravity, where it's coming from. I can use a plane to say where it's coming from and use component sets from there. For this, because we're talking about this as an overall affected system by gravity, I'm just going in Y, and it's going to use the world frame. We can change that numerical effect. So if we were looking at a mass spring damper on Mars or something like that, we can change that to see what type of effect we will be getting. So what I'm going to do is just zoom it out, and then I'm going to run. As you know, there is no damping on it. This thing is just going to oscillate and oscillate and oscillate, just because there is nothing damping this down. If I bring this back, we're set to 1, and now what I'm going to do is introduce a damper. So my linear damper, I'm not going torsional dampers because obviously we're not a torsional effect, we're a linearization effect, so I'm going to come from the top and then do the same thing again. Now again, this is the one thing that always frustrates me, that this is a visualization system that doesn't visualize the effect of something being there. So in other words, it'd be nice to have, even if it's the world's crappiest damper drawing, to give me an idea of where that's sitting. Now what the damper does is the same thing as the spring. It takes the center of the surface, center of the target, and places them in between it. However, gives you no indication to it, and that can often be a little bit frustrating. So I'll click OK, and I don't know if I click on there, but if I click on the spring, oh, the spring stopped displaying as well. That's a frustrating one. I can right click on it to actually show the spring and go on to edit, and then I'll see the spring. But the damper doesn't show. Small things, but it is just one of them little things it'd be nice to be able to see. So I'm going to hit run again. Now what we're going to do is just study the effects of what these two key components actually do. So if we look there. Now again, we're getting a behaviour now. What I now need to do is that I've got all my key components in effect. I've got, let me bring this back. I've got my key components in effect, and really I've just picked random values off the shelf to give me particular behaviour as a response. Now I'm in a position where I need to start tuning and looking through what type of accuracy this is already set to. Now when I refer to accuracy, I'm just going to call up an example what I meant that we were covering last week. If I can actually find it. There we go. Now this is what we're solving. If you consider this as a time step, the real learning side of this was just simply these iterations, these processes of iterations. Each dynamic system will be dictated to by these iterations. And what we're going to do is just set these iterations and just look at where these are found. So these iterations will define accuracy. They will also define the amount of time needed to run something, or the how big this simulation will be set to as a result. So let's look at the motion properties. Now the frame rate of a system, what it'll do is it will attempt to use the frame rate as a predictor correcting method. It will try, if I set this to 200, it will try to look at the frames in between, then look at the accuracy that it's used, and it will try to change it. Now there's a real good way of showing you this, which I am going to show you in just a moment, where you actually look at how the system was recording it, and it is really interesting to see how it does it. So what I'm going to do to make this even more accurate, I'm just going to set this to 100 frames. So as it runs, it'll go one frame, another frame, and then the accuracy tool, the iterations, so if you consider this to be H from here, our time step, if you consider this to be a time step, what this will do is it will dictate how many times it's run. So it will build, in effect, more lines of that spreadsheet that we're building. So I'll just boost it up by 1. It might have a nightmare now though, just because I'm making it super accurate for a very basic simulation. I just want to check it, so I'll run it to make sure it's going to run. And what we get is this result. So I mean, I can run it again. Obviously I can speed it up, slow it down. Right, the next thing I want to do is I want to pull a result from it. Exactly what is it doing? So, just to stay with that mass spring damper example, I'm going to go displacement, velocity, acceleration. I'm going to go, we'll go linear displacement because we're going to track it against this component. We're going to go in the Y component, and what we will get is absolute. So this position is obviously going to be negative when it resolves. We can go in the magnitude. If we go in the magnitude, what that will do is it will push everything into the positive. So if I click on there, we look down, you can see there where it's marking it from with the white marker. And then all I need to do, I can do a plot time results, but I'll stay with that particular time set, and that's what we're getting. So if I bring that down, so we can see there through linear displacement, it displaces, I mean, according to that, 29 millimeters, so it's full strength. It's almost at 100% capacity of its free length. So it starts off at a free length of 20 millimeters, and then it's almost, well, it's doubled past that. Oh, hang on. Apologies. Yeah, we started at 20 mil. That's really awkward. So we're actually looking at half of its extension. So that's how much it's moved. However, if we're talking about a mass spring damper, that in itself is critically damped. Because it's critically damped, it is not really what we want. What we actually want from this is we want to be looking at this to look at what the effect of both spring and damper do. Now, as we know, spring will contain the energy, so if we disperse it by loading that energy, it will contain it, and the damper will disperse it. So we can operate these two components to allow us to get different types of effects. So if I just minimize the level of damping that's on there, so if I drop that down to 0. Drop it by a factor of 50, if I by a factor of 5, so take it down completely, it's still at that critical element, so it's massively overdamped, massively. I mean, arguably we could shorten this, but what you can see there is the response rate. So what we could really do is pulling out now the acceleration of this, because obviously if we're doing a suspension system, anything like that, we need to be able to control the acceleration of this, and we need to have a good idea of how quick these things are moving. So in fact, I'll just pull velocity, go from the top, and I'm just going to, let's go in magnitude. Well, no, I'll stay with the component sets. So I'll go on component set and then go OK. Yeah, so we have a rise in for velocity. We have a rise to 18 millimeters per second. It's not much at all, but it is still moving at quite a rate for the size of this. Because don't forget, it's only 50 mil. It's only a very tiny thing. So what I'll do again is I'm going to lower that the damping, and I'm actually going to take it quite a bit down. Now if you look there, it stopped. Now that yellow marker will tell me when the system stops. Now because it tells me that it stops, it could be now that we're into a freedom point, and because it stopped, the spring is at its natural full extension. So in other words, the spring isn't strong enough. So I've just risen it. Oh, it's awkward. So I'll rise it up by 2. Right, you swine. Then I should have thought up some good values before I did this, which is awkward. I am still at that. Just stop that. Now I'm going to shorten this down, because if you look there, 0.39 seconds. I just want to look at that effect, because that's an interesting effect there, just there. And what I'm going to do is I'm going to use my zoom to fit, and then I'm going to shorten this time spurt right down to a second, zoom to fit again, and we know around this point here is where it responds, so I'll run it. Now what we're seeing is very similar to what would be almost half critical damping. If we look at this response, now you see these key markers here, and these lines here, and here, and here. What this implies is that there is error in the simulation itself, because if I go back, again I'm not staying with Excel, this is just a nice way to display what I mean. If we think of that between each one of these is a point that is put onto the Excel spreadsheet, all the systems do the exact same thing. So these are points that are put onto it. What this means is that there was a displacement between it where the points could not be quantified, and what you've ended up with is a line there, so that is error in the actual simulation itself. The amount of times I've seen simulations where you've got these, in a lack of better words, little lines that appear, it is scary. And people say, oh yeah, it's perfect. It is not perfect. It is miles from perfect. So what I'll do is I'm just going to try and minimize the amount of computational things that I'll need. I'm going to boost that frame up to 200 and see if that just solves that problem for me. Because then what it'll do is it minimizes the level of oh, yeah, you see it's nearly there, still on there. I can tighten that up with the simulation result. However, you can see there what it'll do is overshoot and then a response to it, and then we end up with this, if you will, major overshoot to point. It's normally about 0.25 of an overshoot between the first to the second response. Now the settle sits at around, where's that set to? Let's have a look how far that is. We could say 0.12 of a second, so that's where the settle point sits. Now if you're designing this for a system like a suspension, what you've got to think about is how quick that settle emerges. Often when you're applying a damping ratio to a system, you need to be sure that when it's been applied, that this will not affect the body itself, because obviously most damping systems like that, like a suspension system, is designed around the ergonomics of a human, and if it's too quick, you'll be introducing forces into the lower spine, which could lead to further complications. If we wanted to drastically affect that even more, we could look at the spring and incorporate a greater spring stiffness to it. So again, I am just being crazy now and just boosting it up drastically. So if I run it again, it may be so strong now that it won't even open. Let me have a look. Yeah, I mean it's not the best, but what we're getting now is it's so strong that we're now inside of that insecurity zone again. If you look here, in fact I'm going to drop that down a little bit more because I'm really keen to see this behaviour. So I'm just going to go back up, I'm going to bring this right down, I'm going to drop to, I'll go 0.2, still give you, see if I go 0.2, still gives it that time to settle at the end, because I'm key to show the settle, but not compromising what we're looking at. Now, look at that. We've got these key points here, 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 here and here, and these are huge levels of errors that are occurring with it. But this is happening because I've made the spring so strong, it's slamming shut in 0.008 of a second. It's slamming shut. So this is not the type of damper that you'd want in your car. This would probably lead to force travelling through particular points, and again probably travelling through someone's backside and leaving them with spinal injuries. So if we want to tidy that up, all we simply do is we go back again. Now if I go to use precise, 2 seconds, I think we've got a question. Come back. Cracking question. Cracking question. Right, so I want to read that out. For the mass spring damper simulation, how difficult would it be to model a rear suspension of the MTB? Oh yeah, for the mountain bikes. That's a good shout. So, actually, very easily is the answer. Now, because you've got to remember, because, in fact, let me just minimise this, because what we're looking at here, I guess, minimise that, that's what we're looking at here, is just a mass. That's all it is. But if you had the frame, what you can actually do is have gravity take effect. You could have a force pushing down on the actual seat itself to equivalent for the body, and you could also have forces pushing up on the rear end of the arm, and then what you'd actually get is responsing coming from the suspension itself. You could tune that suspension, and I've seen somebody before who did non-linear dampers. Now these I don't know who's come across these non-linear dampers. These non-linear dampers are fascinating for what they can do, and I have come across somebody who actually did it on this, which is impressive, very, very impressive. But yes, as an answer, good question and dead straightforward. Dead straightforward. Right, so the other thing I wanted to show you about this, because again this is just me introducing you to this system, let me just bring that across, is how this is exported. So if I go down to my results, you'll notice here it's got my linear displacements on both my X and the Y's. Now, often a lot of people want to be able to take their simulations out and then use them to compare them against the simulated result. Interestingly, I actually took this same simulation and compared the two with MATLAB and this, and they were the same, which was really impressive because MATLAB's quite a big hitting software. However, Dassault systems do tend to have a dynamic thing in the background. Dassault do have a big partnership with MSC, so it was just interesting to pan them off against each other. What I'll do is I'm just going to export one. I want to show you how this has been plotted. So if I right click, I'm going to export to spreadsheet. You won't have these on here, it's just because it's for my research. So I'm going to export to spreadsheet. Give it a minute. And now it's in the spreadsheet itself. Now this is what I was trying to show you all last week. I don't know where we can see this. Look at that. Now I know everybody will look and go, yeah, it's not bad. But if you actually look at what Excel does. So if I scroll down, notice how the lines have been turned into curves. This is one of the reasons that Excel gets a lot of criticism, which I can understand. If you're going to publish, you don't really publish with these types of plots because they do lead to misleading responses. What we're actually interested in is them key points in space. So if I go back to what we're getting on here, at least this system, at least the MSC system, is presenting us with a true response of where the error is there. But if we go back to Excel, it gives you the illusion that the error isn't there. So what I would always say is, when it comes to plots with Excel, again, we only did this last week because I wanted you to get some feel for having to plot every single line on the simulation, and it's, in a lack of better words, it's a ball ache. It's a real pain in the backside. Right, so the other thing I wanted to show you about this is we can see how this has been plotted. So if I come back across and just scroll in. If you look, goes by 5 to 5, then changes, then returns, and then goes back to 5, and it has slight changing in it. This is coming from the frame rate. The frame rate allows you to have this variation, allows you to, what these systems will do is they will run it, they will run the chosen time step within that frame rate to look at its accuracy, and then depending on the result that you're getting will be extended and shortened. This is called variable time step. Hang on a second, if I come back, there is a key variable runge cutter time step that's built into the MSC solver. So if I go back to here again, and in here it's not really clear exactly what's going on with it, but the precision contact between it, and then if I go advanced, I've got a couple of the solver integrations here, but they're not clear. What this actually does is it uses further predictor corrector methods. So in other words, when I come back, it will variantly change that time. Now this is a really common method. Lots of systems have used it. Nastran were the most famous to first introduce this idea. If anybody wants to do a bit of back reading on this method, it is called predictor corrector. And you'll find a cracking read. I say cracking. You'll find a very informative read in K.A. Stroud's. I think it's more the latest version of Stroud's Engineering Mathematics, where he actually refers to the predictor corrector method and how it works. And it's simply a statistic. It'll run through and then find the most closest average to the next oncoming value and then try to match against it. It's a way of convergence, and it's a way to just check that you're getting a value which is correct and the most correct possible. When we're moving on, I am still going to take you through the process of convergence, because it allows us to verify and just check to make sure we're getting a realistic value. So it's something to just keep in mind with that. Right. What I'm going to do is I'll just run that through again. And this time I'm just going to boost my frames up even more. And then run it again. And then you see there, we're starting to remove these errors that are occurring. There's still quite a bit. There's still things that we can chop off, but this just becomes down to time step refinement. So in other words, where we'd seen in this, to get a smooth response, all we did is we lowered that time step. This is the exact same process. In MATLAB, it's the exact same process. Nastran, again, the exact same process. It's all about the time step. The time step is what is in FEA the mesh of the simulation. The iterative process is that meshing, if you will, that resolution of the simulation. So it's vital that you really consider what it is that you're setting up and what type of times that it is that you're using. So let me just save that. Again, if anybody wants to have a crack at building other stuff outside of this and you are interested about setting up something else, I am always open for emails. So if anybody's got some crazy ideas that you're going to try simulating something, please let me know. More than happy to try and help you get it working, because it is a fascinating thing. Stuff that the movement of something and that simulation of looking at what's going on, it is really, really fascinating. Right. So let me I've saved that, and what I'll do is I will be zipping that together, just because this is a piece of geometry and also the assembly. So I'll need to put all that into a zip file. I'll put that into a zip file and then I'll stick that onto Teams, and then you've got access to it. Right, so I'm going to close that, save all on that, and what I want to do now is move on to, oh, not that. What I want to move on to is, where are we? Oh, that is a bummer. I had honestly thought that I downloaded everything. Have I downloaded everything? No. Right, here we are, here we are. So what I want to move on to is the wheels. Now this, I've tried to verify through my simulation aspects and through my calculation how this thing is solved and what we were doing. Now this is an old school method. What you'll notice here, for anybody who's looked, what you'll notice here is I've got a fixed material made of plain carbon steel, and it's actually fixed to a plate. Originally in most Dassault systems and in fact most CAD systems, you had to have a fixed point for this to interface with. Since then, that's now changed, and this can be simplified even more. In your assignment, when I set you this assignment, I'll be looking to see of your simplifications. So in other words, if we if I give you a ridiculously complicated geometry, which I'm gonna, and you put every single component in it, my ultimate question is going to be, did you need everything? Is all that geometry really needed? It's not about the modelling, not about the modelling. This is about assembly parts, and were all these independent pieces of geometry actually needed or not? So that's what that is really going to be looking at. And in this case, I'm going to simplify this. I'm going to take you through the simplification, and it's nothing major, but it's a great start to show you the type of thing I'll be asking for. Now, if anybody's interested, on Blackboard, you'll find something called wheel models. We've got wheel 1 and wheel 2. I've left this in a raw format because that wheel 1 and wheel 2 will also work in MATLAB Sim Multibody. So again, if you get a chance, take a look at both, see which one you like. Again, drop me a message if there's something annoying you, something you don't like, let me know. I'm gladly, because I do find simulation is very much a you either love it or you loathe it. So I'm quite keen to help those who are keen into simulation and want to get moving forward with it. Right, so what I've done is I'll just cancel that. I've gone to new assembly, and all I'm going to do is I'm going to import. So here, this is what's common with the systems. I often think, why not just have it all up so I can just grab it? But anyway, I'm going to go to SolidWorks and I'm going to drop it, and I'm going to go to step files. So these are my 2 step files. What we'll first do as a consideration is we're going to look at wheel 1. This is wheel 2. So I'm going to look at wheel 1. Click open, and it will process that. Now again, this is actually relatively brand new. This didn't used to happen. You used to have to build the bloody thing and then build it into the simulation, build it into the assembly. It was an old ordeal, it really was. So I'll click OK on that. Oh yeah, do you want to render it? Yeah, whatever. And now what you'll see is you've just got the basic part in there. If anybody's wondering how I'm navigating, by the way, it's through a 3D Connections mouse. If you are a CAD savvy guy, I would recommend that you use one, because they are amazing. Right. So as like on the mass spring damper, I'm going to build this wheel sim. I think what I'd like to do first is set this up as wheel sim. And let's first introduce it. So, like on the first one, first thing that comes in is always fixed. So I'm going to float it. And to show you what I mean, if there's my origin, I can move this wherever I want to go. So it's free to move. That will tell you if it's floating. If it's fixed, you'll drag it and it just won't move. So what I now need to do is to place this wheel on an axis. I'm interested. What I'm actually studying in this, I'm studying the. I'm just going to study the effects of gravity on different scenarios of this wheel and how it functions. The whole notes on this is really about gravity and how gravity affects the wheel itself. So what we're going to do is we're going to set this. So I like to stay quite close to the notes as well, because you guys all have this as well. So what I'm going to do is I'm going to go right plane, press Control, select top plane, and then I'm going to go to reference geometry and axes. That then defines my axes. I then go mate to the internal face of the wheel. Make sure it's concentric. Click apply. So at this point, it will freely move around the axes of what I just set. Now, what I really need to do is I need to set the backside as well to the right plane. So I'll do the same thing. Go to right. Oh, I nearly made an epic mistake then. Front plane in my case. Oh, so I'm going to go to front plane and then constrain that back plane. With that set, I've now got freedom to move around the axes. This is now free to move, and I can do, I can do my sims and get results from it. Now, I'm just conscious, what material did I use? I think it was plain carbon steel in this. So I'm going to right click on here, I'm going to go down, go to materials, plain carbon steel. And a lot of people like to see these things moving, like to know that these bloody things move, or else you don't know it's moving, which gets annoying. So what I normally do, and I did on these notes, is I painted this front face. So I'm going to left click, I should right click on there, sorry. Go up to here, go to appearance, I'm going to click on appearance. Now under appearance now you can go body, you can go the wheel itself, you can go the imports, or just the face. So I just want that face. Then what it does is it comes up and says, do you just want to texture it? So I go, yeah, just put me some texture on there, and I click OK. And now what it means is when it moves, you see that texture moving. It gives you an insight to this thing moving. Again, it has helped a lot of people before be able to visualize these things moving. But if any of you have been following up the MATLAB as well, you'll know that you need as much as possible to understand if the object is moving or not. So what I'll do now is I've got everything set in position. I'm going to move towards my motion analysis. I'm going to drop it. Go to basic motion. Motion analysis, sorry. And then I could go on to motor. I could set this to a motor. This software, by the way, is great to test if a stepper motor, if a DC motor, if a servo motor will deliver on a job. If you know the output of that motor, you feed it into this and you have gravity affecting on it, and you can actually see how well it's going to respond with whatever your target's going to be. I've had students who've done all sorts with these motors before, from robotic arms through to power output for a drone, through to electric output for electric go-karts, things like that. I've had all sorts. So I'll go to force. I'm going to apply a torque. I can select the face, I can select the outside here, I'll select the inside. fact, no, I'll select that face. Oh, I'm making that very hard work there. I'll go the outside of the face, just to stay consistent with what you guys have seen. So I'll stay on the outside of that face. And we're going to move around in this particular direction. And the output, based on the forces that I've given you, is 1356 Newton millimeter. 1356 Newton millimeter. Okay. So, I can't remember what time I set for seconds. So we're going to 0.008 seconds. So I'm going to bring that right back over to there. And I'm going to just zoom in. It's a very short amount of time. Just about there. So where we are. Right, so we're actually running that amount of time. So again, I'm going to hit save. The one thing to keep in mind is the more elements that we bring into this, the more calculation that's going to be needed for this to be able to calculate successfully and for it to be able to give us a good working value that we can operate to. So what I'm going to do is go calculate. Oh yes, see here, now it's saying that the frame rates I've got set are too small, so it's recommending a frame set. And speed will be set to 5 seconds. No. But what I am going to do is go back again and just look at my frame set. That's I've just set that. There we go. So what I'm going to do is just go and look at what frames are set at the moment. That is something I didn't do. So what I'll do is set these to something large. I'll go 5,000. Now the reason I'm doing this is because I know the amount of time I'm operating in and the accuracy I'm running at. If I'm running 5,000 frames per revolutional set, this will then be able to calculate motion around them frame sets, so it becomes scalable, if you will. So if I run it, still not happy with me doing that. No. Why is my axis doing that? My axis should not be moving. Okay. So now, we're just going to look at linear acceleration and we're going to look at linear velocity. Wow, I'm being messages like mine there. Right, so if I go to plots, I'm going to come onto my plots and I'm going to go to displacements. Oh, I've just realised a component. I've just realised a question problem there. Anyway, so I'm going to go. I'll go linear acceleration. I think it should change itself, and I'm just curious now. And I'm going to go within the Z component. Did I tell you within the Z component? I did. Good. And I'll come from this face. Oh, maybe not that face. Apologies, I'm just trying to show myself that which face I chose. Because I'm not on linear, there is a problem. I just want to show you that's what I've. These are the notes I've put on there, so I'm asking you to look at angular acceleration, and I've actually put linear as a chosen point, and it's not linear, it's angular. So apologies for that, and I will fix that today. That's very awkward, but anyway. So let me come back. I'm just gonna, I think just for completion, I'm gonna delete that out completely so it's gone. And then I'm just gonna reset that again. So I'm gonna go back to my graphs. I'm gonna go to linear acceleration and velocities. Now I'm gonna go, angular acceleration. I'm gonna go around the Z component. And I'll choose the inside of the face and let's see what we get. That's a little bit more like what I was hoping to get. Bring that into there, like that. And then I'm going to do the same thing on my angular my velocity. So I'm going to come back in, come back across, and go velocity on the Z component coming from this face, then OK. Yeah, there's going to be nothing around that, is there? I'm going to take him from that face. Let me come back to my angular, got to edit that feature. And what I'm going to do is not come from that face, but come from that face. That should give me something. That's actually giving me back a roll. It's because I'm coming around. Oh, it's because of my angular velocity. Go to there. Z component. Right, that's better. I wonder why it wasn't giving me anything then. It's me hitting the wrong button. So what we're getting with that now is we're getting that angular velocity increased. Now the thing is with there being no gravity at this point, what you're actually getting is a linearized response from the acceleration. That's all it knows. We've started this off, and the gradual build from the angular velocity is, as you'd imagine, it's going to be gradually building up because it's got to overcome that initial momentum. So what we're going to do is introduce gravity onto this just to see what type of effect it will have on it when we run it. So let me just come back, and I'm going to come here and then put these both side by side, and then what I'll do is come back up here, and what I really want to do now is I want to push my simulation board right back to the beginning. And I will now drop in my gravity, because as you can see at the moment we're actually running this as just a bare system, so it runs at 0, which is not a true representation of what's going on. So if I now run on gravity in my Y component, running at 9.81 or 9.06 to whatever decimal place we're referring to, if I run it again, and I'm not running it to 5 seconds, just because I would just want to run on the criteria that I talked about. Now interestingly, the initial effect of what we're getting is very little. There's slight noise that emerges, and that's just the initial momentum that causes from it. So this sim in itself is not affected heavily by gravity. I have tried to offer some mathematical verification in that when we come to here to show you initially what the types of values that this can do, and if it's under gravity or not. So if we're not under gravity, we have a linear response, and that's what I'm trying to work to here. Now what we can do is bring in the second wheel. We can look at that second wheel to see what type of effects that will have. What I'd like to do first though is just look at introducing a variation in this time stepping. So what I mean, not in the time step, in the force itself. So what I mean is we're going to set a particular output for the torque. Now normally when you're setting out these torques, you can set them linear. So if I go onto my torque, in fact let me bring this time step right back again. If I go back to my torque and then go edit, what you can see here is we've just got the stand output force parameters. So we've got a constant value that's occurring. We can have all different types. We can choose expression for the output. We can choose all sorts of types of output for this type of example. what I'm really keen to do is introduce the idea of having a variation that's there. So what we'll do is we're going to set a force on function. So if I go to constant force, and we're going to set it oh, they've actually changed the name. So you see with steps, as you see there, I can actually change the force this way. It actually used to be called by full function. Oh, it is still on force function, but in this case we're now looking at a step. Now what this step will do is it will start at a particular value at the first point. Then we can say at this time be set to this value, and then at a particular time after that, so in my case I'll set to 2. I can set this to 11.23, just as the pre-example. Click OK, and then run. Oh, I've set it to 5 balls. Yeah, because it's slow increase with it. Right, so yeah, it's only just starting to move at this point, so that's why I've just thought I'm now introducing a bit more time onto this. So I'm going to bring this back, and I'm now going to set this somewhat bigger. So I'm now going to set this somewhat bigger to more of 8 seconds. And what this will allow it to do now is build. Trouble is now, with me setting this bigger, it now starts to take a lot more time for this to be solved. Now these systems, you can turn off the animation. The animations often can give you an insight as to whether these things are running correctly or not. I suspect by me setting this to 5,000 frames is perhaps a little bit too much. So 2 seconds, let me just minimize this. So if I now set this to 2,000 frames, or maybe even less, I'll probably just go 500 frames. Because I want to make sure that this is running like I want it to. So if I run it, this is irritating, because that gives it the appearance that it's bouncing, but it's actually not bouncing. There is an inconsistency there. That's probably coming from my system setup. So see there, it's continuously running, it's now running under gravity. That effect is just building up to that particular speed. The velocity and acceleration should be fixed, and it should now be responding like I want it to. Right, I'm just going to stop that. Now, as you'd imagine, when we look at this, we get that initial momentum of build. It needs time to actually get an initial response based on the velocity. If you have however, you look at the acceleration of this, the acceleration builds up slightly quicker, but it still needs to come it still needs to overcome the momentum of the system. Hence why it will just build up, and then reach steady state speed of its acceleration, because it's what we'd set it to. If I now bring this back, and let's say for this example, now we're in a position of where what we actually want to do is we want to run that to a particular time and then chop it off, and we want to look at that effect. I mean, what we could do with this as well is I can just simply suppress gravity. And if I suppress gravity, if we look at the outputs it's giving, I suspect it's not going to give me much difference, but it's nice just for consistency, just to see the types of effects that it's getting. So we're reaching a maximum of 1324 degrees per second squared. if I run that, now I'm hoping it's going to give us something that is going to really show what gravity is doing to it. That is really irritating. Right, so I'm at that there now. If we look now, these two become spurts between them. We've got a velocity which is easy to overcome the actual mass itself, so it does build a lot quicker, a lot sooner. And the acceleration with it just shows really that we're looking at is very little effect coming from gravity. It's all coming from the initial force that we're applying to it, which I know what you're thinking. It's quite obvious that that's occurring, but it's nice to be able to just dissect that and just take a look at actually using that. So if I bring this back again, but this time I'm going to drop in gravity, and also on this segment now, what I will do is I want to look at how quickly this system can respond if the motor is shut off. So you notice where I brought my cursor, I bring my cursor over the 4 seconds, I'm going to right click and I'm going to go off. What that actually does now is it will run that torque to that time, then shut it off, and I can see, keep getting that game thing coming up, I can see what type of effect it will have. So if I now hit run again, let this run in. I suspect I'm running perhaps a frame rate that's too high, and I'm putting mass levels of complication on that. But I just want, I'm really considering more my results. Really what I should start to be doing once I'm happy with them results would be to start looking at bringing that time step down to actually make this a bit more easily accessible and more easily runnable, because at the moment, as you can see, it's taking time for this to be simulated. I mean, this animation frame set here does not control the speed that you run at it, so what it will do is it will just keep running. So now I've run past that 4 seconds. I'd like to take it to 8 seconds, because what it will allow me to do is just see the effects of literally chopping this in two and looking at the acceleration. Now I suspect with the acceleration what we'll genuinely get is it's just returning to zero, as yes of course it'll return to zero, and then the momentum of this drive has just continued and it's still not steadied itself out. This is where we start to hit limitations in the systems like this, which can irritate me quite a bit. Of what is presumed on this at the moment is that as it runs, there is no friction between the axes, there is no friction on the wheel, on the ground. This is just purely examining the effects of adding torque and what type of effects it has on the system by us looking at gravity and us looking at variations of inputs from the system. So there is ways to consider a little bit more friction, and we will need to add friction into things, because I think any type of simulation that you run, if you've got friction, it needs to be there and it needs to be considered, because it's everywhere, it's in everything, and it would be crazy not to. Right. So finally, what I wanted to do is to simply change this wheel over. We've got this sim, we've got an initial type of result. We know that this now will not be truly affected with it. What I could do is, if I go back into, now I think this is in here, I need to double check. we do have load-bearing faces. Now, as I said, when there's more components onto here, we can add further things into it. We can add reactions into it. Again, because it's a single component, it becomes quite tricky to be able to do that. What I will be showing you though is what's called contact mechanics. Now with it, as we move on, we'll be looking at the coefficient of friction between two particular materials. With this you can set it by, if you're saying look, it's like a rubber and a steel, and it will try to give you a rough coefficient of friction. Or if you know what that coefficient of friction is, which is even better to be honest, you can define that by dropping that off, by saying look, I don't want you to consider the material, I want you to consider the friction and the static friction of the material. Or you can do like I've seen a lot of people do, go, it's a bit sticky, it's a bit slippy. So that's one thing I don't really like, but it is important. Then the way contacts will work as well is you've got your restriction, your coefficient of restitution. So the bounciness of a component, we will look at that as well, because there's some key elements about that you need to know. The biggest thing that affects every single simulation that we run is that resolution. Everything will get wrecked in that resolution. Just checking to see if I've just had an update. Is there a question? No, just double checking. I like to make sure that I've covered all questions. I don't see any new questions. No. Right. Apologies for that. It's because I'm on Teams as well. I also get updates from random things that are going on. So we can do more with this. There is more and more things we can do with this. The thing that I don't like is air resistance needs to be modelled with linearized forces, which I still don't think is a good recommendation with it. So I will frown away from using that quite a bit as an active component. I will be focusing more on your closed mechanical system like a piston, things like that. This was just to introduce you to the idea of being able to navigate around it, pulling values out and looking at the types of results that you're getting from that. Once we look at the second set, so this is just a single wheel. What I'll do is I'll show you how to change that wheel and show you how to set up the second wheel, but then what I would recommend is that you have a go. So what I'll do is, when I've got this, there's a few things I can do. So if I hit save first, now I can either replace this component completely, or I can bring in the wheel as well and suppress this and attach that wheel to there, and then just attach it that way. So I'll try both ways. So if I go insert, in fact if I just select the part and then I go edit, where is it now? I always forget where this is. I think it's on here. There it is, yes. So you see here at the bottom where I've got replace. I can go replace on components, so I'm going to change my best from the tree, so change that one. Browse for my newer one. Now I bet you it's not going to allow me. Oh, that's a shame. That's because it's an import that I was using, so that's a shame. So I'm going to have to actually make this other one. So what I'll do is just simply open the file, wheel 2. No, I don't want to use diagnosis. Again, with this, I'll just set that material. So I know it's a plain carbon steel, and also on here, I'm going to set that to my face, and I'm going to texturize that face, and then click OK. And then from there, I'm just going to save as, stick it in that same folder as wheel 2, and then I can close that down. So on here I'll go replace. Now I can choose this component and I can browse for my replacement, which all files is wheel 2. Now it's interesting how this is going to be introduced, so let's see. Yes. Then click OK. So now it brings up the compliance. It's saying it's got replacements for it. It's saying that I've changed an awful lot and it is incorrect, so I need to fix it. So all I simply do is go close and concentric between that and. So let me just find the right bloody one here. That's why. Let's have a look. Now it asks me, where is that one? So this one is now on that side. Oh, this one is on that side. And I'll click OK. And then that should be gone. It is gone. So all I was doing is just changing it around so it could run again. And all I've done now is replaced it. And if I run it back in, it'll go, new component, what are you doing? So we look at the outputs and then run it again. Hang on a second. As that replaced, look at the torque. The torque looks like it's deactivated. The torque is deactivated. Oh, that did not work out like I wanted it to at all. So I'm going to edit. Ah, yeah, you see there? Essentially what's happened here is it's come in and just gone, nah, can't do that. So I'm going to click on that face again, and then I'm going to go run. Now if I run it again, it should start to respond. It better start to respond. I think that shadow is actually coming from the way it's drawn, and it's not updating the way it's been drawn. And what it's doing is every time it's spinning round, it's seeing it in like as if it's stationary. I think this is because the model was actually drawn in an older version, which is a bit crap, I know, but that's in essence where it's coming from. Now you notice on this one is far larger. So with this one now, it almost returns to a dead state or a stationary state much quicker. However, look at its ability to resist the overall. Now this is simply the mass that is restricting the actual motion of it. Again, no friction. There's no restrictions around anything else. But you can see there that as it spins, because this wheel would be in this case quite balanced, what it does is it almost looks to slow down, speed up, slow down, speed up. And if I turn gravity off, what that will do is it will encourage a continuous spinning because there's nothing to bring it to rest. So you look there, you can see there that obviously our acceleration in this case was going to be lower. We've got a large wheel, large mass, but we're running at the same forces that's on it. What we could do from here is, what we could conclude from this really is that obviously if it's bigger, it's not going to run as well. If it's bigger and heavier, it's not going to run as well as the smaller component sets. But what we're able to really do with this now though is we've set up the base foundations to do greater things, to do bigger things. We can introduce reaction forces. I did set a simulation assignment on this a number of years ago, and it was from a guy from Blackpool, and he worked on Blackpool Pleasure Beach, and his focus was around the rose joints of the carts when they're interacting. And what he was doing is he was looking at the resonant frequency of the rose joints as they're interfacing, and he was just basically pulsing both sides. And because it was such a closed system and it was really looking at how well it was deflecting, he actually dropped in a little bit of FEA on the top of it to show where particular points could be failing. And that was a cracking example because he started off with basically ball in a joint, then moved to the next phase of your typical rows, then looked at the coefficient of friction between these two interfacing together, and then dropped in the complication of the real values he was getting from testing from work. But what he did is he started off with a very, very bog standard, really, in a lack of better words, what we would know as just being a crappy simulation to get everything in position. Then he moves to the next phase, which is a good practice. Now, I don't take you through these very basic sims just to insult you or irritate you. The reason I take you through these best sims, it is genuinely a good practice to set up a basic running sim to get them fundamental systems in place. Then once you've got them fundamental systems in place, you can move to that next phase. Again, this is just a wheel, and this was just more of a navigating your way around, showing you how to extract these results, showing you how I can take that through to Excel. I mean, you don't have to use the values in Excel, by the way. You could also extract them values, put them into MATLAB, and actually plot a numerical solution in MATLAB and try and map over the top the two values that you're getting to see if you can actually verify them results. Again, don't mix up the two terms. Verification is doing the numerical calculation to simulation and then showing correlation between the two. Validation is taking your either numerical solution to physical testing and show correlation over the two, or modeling to physical solution and showing correlation over the two. Don't mix these two up, because if you are on your final year and you're writing up your thesis, these are the types of things that a lot of the your supervisors will be looking for if there is inconsistencies or if it's poorly been executed. So keep that one in mind. Keep that one in mind. Right, as I've said, I'm going to save this. Rebuild and saving. Yes. I'm going to save this. I'm going to save this with all of the models and everything that I've done here. I'll save this, put this into the folder. I'll zip it all together. I am going to stick it onto Teams. The other thing is just to reiterate, everyone who is industry based, I will be getting that MP4 conversion for you today. It shouldn't take me too long, just because everything's stored on YouTube, and technically I can download it and then get it to you that way. So don't worry with that, I will get you them backups. I'm glad that you've let me know now, actually, just because it means that there's still lots of flexibility for everybody to catch up with what's going on. I didn't realise, I came across it. Well, yeah, I just didn't really properly realise that that was such an issue. But yes, I will fix that for you all. I don't want to drag too much time of just looking at this again and again. I just wanted to take you through this. What I will be doing is I do have loads and loads of nodes in both MATLAB and in this. And I'm just going to try and keep uploading more and more and more. Now, what you will find is there is a lot more tutorials out there to support using this. There is an awful lot out there. Now, this is purely because I hope I can show you this. Let me see if I can pull it. No, it's probably not actually on. I'll have to find out where you can find it, but it gives you a full detail of where the solver's coming from. And that's why there tends to be a lot on this, because obviously it's good business for Dassault, it's good business for Nastran, well, for the MSC software company, because they can really promote what it is that they do and how well they do it. With the MATLAB multibody, it's such a vast void of different tools that it can use, that there is stuff out there, and there's just not a lot of it. I do try to produce as much as I can as well on it to try and help anybody else along, just because it's a phenomenal bit of kit to be able to use. So again, I will stop recording.